Welcome back everyone to the Forum for Learning and to part 7 of lecture 2 in the Biology 101 lecture series. So in this video we'll discuss what are moles and Avogadro's number, we'll discuss what acids and bases are, and then we'll talk about pH and why it's so important in biological systems, and we'll finish off by discussing what buffers are and how they work. So without further ado, let's get started. So how do we quantify things in chemistry, right? There's a couple ways to do it, and we'll talk about a few of them. So the first one is using the concept of the mole. So the mole, so let's write that down. So what is the mole? Well, you can also see it written like that as well. So what is a mole? So a mole is the amount of a substance in grams that is numerically equal to its molecular weight. Okay, so let's write that down. So it's the amount of a substance in grams that is numerically equal to its molecular weight. Okay, so let's look at a few examples here. So what do we mean by mole? Well, in 1 mole of hydrogen, right, the hydrogen molecule, you have two sort of atoms of hydrogen, right? So you have two hydrogens, and each hydrogen atom weighs about 1 gram, right? According to the periodic table, the atomic weight of hydrogen is around 1 gram, so we'll say that. So that's 2 times 1, you have 2 grams. So 1 mole of the hydrogen molecule is equal to 2 grams. All right. So again, so the mole is the amount of a substance in grams, which is right here, that is numerically equal to its molecular weight. So molecular weight there. Okay. So let's look at another example. So 1 mole of sugar, C6H12O6. Right. So here we have 6 carbons plus 12 hydrogens plus 6 oxygens. Right. And that equals, so 6 times the atomic weight of carbon is right around 12 grams, plus hydrogen, which is around 1 gram, plus oxygen, which is around 16 grams. If you add all of that up, you get about 180 grams. So 1 mole of sugar is around 180 grams. So again, a mole is the amount of a substance in grams that is numerically equal to its molecular weight. Okay, so that's one way to quantify things in chemistry. Now let's look at another way. And the other way is called Avogadro's number. Okay, so what is that? Well, Avogadro's number is a specific number, and it's 6.02 times 10 to the 23, right? That's Avogadro's number. Now, what's the significance of Avogadro's number? Well, the significance is that 6.02 times 10 to the 23 represents the number of molecules in 1 mole of any substance, all right? So this number represents the number of molecules in 1 mole of the substance. Okay, now, the important thing to note here is that this number is the same across all elements. Okay, so what that means is 1 mole of salt will contain the exact same number of molecules as 1 mole of sugar. Okay, so this number again is the exact same across all elements because it represents the number of molecules in 1 mole of a substance, right? And all molecules, 1 mole of any substance will have 6.02 times 10 to the 23 molecules per mole. All right. So therefore, the number of molecules again in 1 mole of any element is constant for all elements. Okay. So the mole count and Avogadro's number apply to kind of all different phases, right? So liquids, gases, and solids. But now let's talk about how we quantify solutions. Okay. Now solutions are a little different. So for solutions, we discuss it in terms of molarity. Okay, and molarity again is used to describe the concentration of a solution, and solution again being liquid, right? So let's define this. It's a mathematical formula. So molarity, capital M, is equal to the number of moles of a solute divided by the volume of the solvent in liters. Okay. Now, in part 6 of lecture 2, we did go over what solutes were, what solvents were, and what solutions were. So if you guys want some definitions and a better idea, you might want to check that video out. But let's continue. So molarity, again, describes the concentration of solutions. Right? And again, it's the number of moles of a solute over the volume of a solvent, and it's particularly in liters. Okay? So what does molarity mean, basically? Right? Again, it basically discusses how concentrated a solution is. So the higher the molarity, that means that the more concentrated the solution is, and so the solution is stronger. Okay, and conversely, if a solution has low molarity, that means the solution is weak because the solution isn't as concentrated, right? Because if you have a high molarity, that means you have a large number of solutes in very little solvent, which means it's very concentrated. Now, on the flip side, if you have low molarity, that means that you have less solutes in more solvent, which means it's more diluted and it's less concentrated. Okay, so that's kind of how we quantify things, or one of the ways we quantify things, or I should say a couple of the ways we quantify things in chemistry. And again, with respect to the mole, Avogadro's number, and molarity. So now let's talk about what's next. Let's talk about what are acids and bases. Now let's talk about acids and bases. So there are a couple different definitions of acids and bases across chemistry, but for the intents and purposes of this video and kind of biology, the biology lecture series as a whole, we'll discuss acids and bases with respect to the Arrhenius definition. Okay, so acids, according to the Arrhenius definition, are substances that, when dissolved in water, will release hydrogen ions, thereby increasing the hydrogen ion concentration in solution. Okay, so acids, so when dissolved in water, will release hydrogen ions, or H plus ions, ultimately increasing the hydrogen ion concentration in solution. Okay, so an Arrhenius acid is the substance that, when dissolved in water, will release hydrogen ions, right? And ultimately increase the hydrogen ion concentration in solution. Now, let's just define what hydrogen ions are, right? So if we let's look at a neutral hydrogen atom, right? No charge. Hydrogen has an atomic number of 1, which means we have 1 proton, a mass number of 1, which means that we have 0 neutrons. And if this hydrogen atom has a net neutral charge, and we said that protons have a positive charge, that means in order to cancel out to a neutral charge, we have to have 1 electron, right? And that's a negative charge. So in a neutral hydrogen atom, we have 1 proton, so 1 positive charge and 1 negative charge. They cancel each other out, and you end up having a neutral hydrogen. Now in this case, we have a hydrogen with a positive sign, right? So it's a cation, which means that here, so if it's positive, that means we still retain the proton. We still have no neutrons. But in order for the hydrogen atom to go from a neutral charge to a positive charge, it needs to lose that negative, right? So that means it has 0 electrons, right? Because if it still had the electron, it would be neutral, 0. But because it's a positive, that means there's more positive charges than negative charges. And if there's only 1 positive charge, that means there has to be 0 negative charges, right? So ultimately, a hydrogen ion, H plus ion, is just a proton, right? Because that's all we have left. So that's just a definition of hydrogen ion. So let's continue with acids and bases. So acids can be, we can split acids into 2 categories. Okay, so one is strong acids, and the other are weak acids. Okay, so what are strong and weak acids? Well, strong acids are acids that dissociate completely, resulting in the release of lots of hydrogen ions, right? So strong acids will dissociate completely. Now, we talked about dissociation and water's ability to form spheres of hydration in part 6 of lecture 2, so if you guys want to learn a little bit more about that before proceeding with this video, I highly recommend checking that one out. I think we discussed it towards the end of that video. But anyway, so strong acids will dissociate completely, and what that means is they'll completely dissociate into their ionic constituents, right? And so that results in the release of lots of hydrogen ions. So let's look at an example here. So one example is hydrogen chloride. So when you put hydrogen chloride in water, what happens is, or rather hydrochloric acid, right, in solution in water, this hydrochloric acid will dissociate into the H plus ion and the chloride minus ion, right, or the hydrogen cation and the chlorine or chloride anion. And this happens completely, meaning all of this will dissociate into this and this, right? So because hydrochloric acid is a strong acid. Okay, so a couple of other examples include H2SO4, which is sulfuric acid, and here there's 2 hydrogen ions. Sulfuric acid can actually release up to 2 hydrogen ions because it has 2 of them. Okay, so those are strong acids. Now let's talk about weak acids. So weak acids, they don't dissociate completely, which means that they only release some hydrogen ions and they retain the original structure. So weak acids do not dissociate completely. Okay, so only some of those weak acids will dissociate into the hydrogen ion and its constituent other ions, and some of those acids will remain and retain their original structure. So we said, for example, that strong acids will always break down completely, meaning every single molecule of that strong acid, when placed in water, will split up into its constituent ions, right? It'll go to 100%. It's complete dissociation. Whereas weak acids, some of the weak acid will dissociate, while others will retain the original structure. So let's look at an example. So an example is carboxylic acids. It's an organic acid, right? So carboxylic acids have the structure of this. So it'll be carbon, double bonded to an oxygen, single bonded to a hydrogen and an oxygen, right? Now this is what's called carboxylic acid, and here this is a weak acid. So what'll happen is so let's do it this way. So it's fine. Some of it will dissociate into O minus and H plus, right? So some of it will dissociate into this, releasing some hydrogen ions, but some will also retain this original shape. Okay, or this original structure, so which means they won't dissociate. So there's partial dissociation between the molecules. And so again, weak acids, they don't dissociate completely, which means they only release some hydrogen ions, as is the case if it was to dissociate, but some of it will also remain in its original substance. The original substance will also remain. Okay, and this is carboxylic acid. So a couple of other examples include H2CO3, which is carbonic acid, and CH3COOH, which is acetic acid. the same principle applies because they're weak. These two are weak acids. Now I know there's two hydrogen, right, atoms in this carbonic acid, and we said that sulfuric acid also has that, but sulfuric acid, because of the properties of it will dissociate completely, whereas this will just dissociate partially. All right, so those are what acids are, and that's a different distinction between strong and weak acids. Okay, so now the key takeaway from this is that the stronger the acid, the more hydrogen ions it will release. Okay, so again, the stronger the acid, the more it dissociates completely into its constituent ions, and the more it dissociates into its constituent ions, the more hydrogen ions will get released. Yeah, so that's really just acids, or the Arrhenius definition of acids. So now let's talk about the Arrhenius definition of bases. So bases are substances that when dissolved in water will release hydroxide ions. Okay, so bases are substances that when dissolved in water will release hydroxide ions. Actually, let's write this down. Hydroxide, it's right here. Hydroxide ions. Hydroxide ions are OH minus ions, okay? So again, bases are substances that when dissolved in water will release hydroxide ions. Now, the important thing about these hydroxide ions is now because these hydroxide ions are negatively charged, so OH minus, they can combine with the hydrogen ions that acids release and form water. In other words, they can neutralize that hydrogen ion in solution and form water. So what that means is that bases can provide those hydroxide ions, which can then combine with the hydrogen ions from acids to then reduce the concentration of hydrogen ions in solution. So these hydroxide ions can combine with the hydrogen ions in solution and reduce the concentration of those H plus ions. Right, because the hydroxide ion combines with the hydrogen ion, they form water, which means the number of free hydrogen ions in solution goes down. Okay, so now bases, just like acids, will have two categories. So we have strong bases and weak bases, and the idea is essentially the same. So strong bases will dissociate completely, okay, into their constituent ions, thereby releasing hydroxide ions, right? So they'll dissociate completely and release lots of OH minus ions, and now these OH minus ions can then go on and accept the hydrogen ions in solution, again thereby reducing the concentration of hydrogen ions in solution. Okay, so they can donate hydroxide ions and then ultimately accept hydrogen ions and neutralize them in solution. Okay, so now so let's look at a couple examples actually. So one example is sodium hydroxide. So sodium hydroxide in water, what's going to happen is sodium hydroxide is going to break down into sodium plus and OH minus, and again, because it's a strong base, it's going to dissociate completely, meaning all of the sodium hydroxide ions in solution will then break apart and form the sodium plus ion and the OH minus ion in solution. Okay, so again, they can completely dissociate, meaning all of the molecules will break down into their constituent ions, releasing OH minus, which can then go on and accept hydrogen ions, and thereby reducing the concentration of hydrogen ions in solution. Another one is barium hydroxide, and so on. Okay, now weak bases, on the other hand, just like weak acids, will only dissociate partially. Right? In other words, they do not dissociate completely. Okay, they do not dissociate completely, and which means that they can only release some hydroxide ions into solution, which means they can only accept some hydrogen ions. Okay, so it's similar to acids, just that acids release hydrogen ions and bases will release hydroxide ions. Okay, and the same thing applies. The stronger the base, the more OH minus ions it can release into solution. Okay, so now let's talk about acid-base reactions. So how do acids and bases interact with one another when in the presence of water? So now let's talk about acid and base reactions. Okay, so acid and base reactions can either be reversible or irreversible. Okay, so the ionization of strong acids and bases in water are irreversible. Okay, so irreversible, in this context, are reactions that involve the ionization of strong acids and bases in water. Okay, so the ionization of strong acids and bases in water are going to be irreversible reactions. Now what that means is the reactions are going to proceed in one direction and one direction only, and it's going to go to completion. So let's look at an example here, right? So say we have water, and we have hydrochloric acid in that water, right? Which is a strong acid. What's going to happen is this hydrochloric acid is going to break up, and you're going to have chloride minus, and this hydrogen is going to also break out, and it's going to go and join the water, and you're going to have what's called the hydronium ion. Now, H3O plus is the exact same as H plus. This is just a denotation difference, or just the way you notate it, the difference in that. So, but they're interchangeable. So basically, you have a chloride ion and a hydronium ion, or the equivalent of hydrogen ion. And this reaction will only proceed in this direction. It's not going to proceed in the reverse direction, because all of this hydrochloric acid, because it's a strong acid, is going to dissociate and form a chloride ion and the hydronium ion. Okay, and the reason is also not just because of the dissociative properties of strong acids and bases, but it's also because of water's abilities to form spheres of hydration and isolate those ions. Now, again, if you guys want to learn more about spheres of hydration and water's ability to do that, I suggest you guys revisit, I think, part 6 of lecture 2 towards the end of that, because we go over that there. And you guys have a better understanding of how water can form these shields are called spheres of hydration, and prevent ions from getting back together into their original starting compound. All right, so that was the ionization of strong acids and bases, and again, it results in irreversible reactions. Now let's talk about reversible reactions. So first of all, reversible reactions are reactions that can proceed in either direction depending on the relative starting concentrations of reactants and products. So again, reversible reactions are reactions that can proceed in either direction depending on the relative starting concentrations of reactants and products. Okay, so now with respect to reversible reactions, the ionization of weak acids and bases in water can be reversible, right? They can be somewhat reversible. So these reactions can be somewhat reversible. Okay, so we have reversible reactions can be reactions where you have the ionization of weak acids and bases. Again, weak acids and bases in water, whereas the ionization of strong acids and bases in water are going to be irreversible. So let's look at an example of a reversible reaction. So we'll look at what happens and kind of how the ionization of acetic acid works. So we have CH3, COH, and I'll draw that. So this breaks down into CH3, C double bond O, O minus, and H plus. Again, same thing as hydronium, doesn't really matter, just for demonstration purposes. Okay, so now this is the forward reaction, right? It's just the ionization of acetic acid. So this is acetic acid, okay? And it'll break down into acetate and the hydrogen ion. Now let's look at the reverse reaction. So here we have, so it's this reaction, but in reverse. So we have CH3, C double bond O, O minus, plus the hydrogen ion. That's going to give us acetic acid, right? So this is, again, this reaction here is the forward reaction, and that is the breaking down or the dissociation of acetic acid. And this here is technically the reverse reaction in this direction here, right? This is the reverse reaction of the ionization of acetic acid. And so this whole reaction, or both of these reactions, can be summed up and denoted this way: CH3, C double bond O, OH, CH3, C double bond O, O minus, plus H plus. So this double arrow denotes that the reaction is reversible, which means it has a forward and a reverse reaction component. Right? It can happen in either direction depending on the relative starting concentrations of reactants and products. All right. So again, the ionization of strong acids and bases are going to be irreversible reactions, and the ionization of weak acids and bases are going to be somewhat reversible. Again, depending in the direction depends on the starting concentration of the reactants and products. Okay. So now let's talk about water and how water relates to all of this. Water is unique in that water can be a weak acid or a weak base, technically and. Okay, so water has the ability to be a weak acid and a weak base, and compounds like this are called amphoteric. Right? They can basically just means that they can be acids and bases depending on the situation. So let's look at an example and talk about what we mean. So water is a hydrogen ion and a hydroxide ion, right? Can ionize. This is the way water can ionize, meaning it can dissociate and form ions in this way here, where we have a hydrogen ion and a hydroxide ion. So here, water can release hydrogen ions into solution. Right? When water dissociates, it can release hydrogen ions, but it can also release hydroxide ions into solution, like right here. Right? So when water breaks down, it can donate both a hydrogen ion as well as a hydroxide ion. And now this hydroxide ion can then go and accept H plus ions like bases do. So this is water's ability to become a base. This is water's basic property, whereas this is water's acidic property. So as you can see, water can act as either an acid or as a base, but it would be a weak acid or a base because of its internal properties. So now the ionization of water, meaning that the dissociation of water into its constituent ions of the hydrogen ion and the hydroxide ion, is infrequent, right? It doesn't happen all that often. But what we have to consider is that because we're made up of 70% water by weight, that ionization, even though it's infrequent, can be significant, right? Because you have so much water, even if one in every 10,000 water molecules will ionize at any given moment, because we have so much water in our bodies, that ionization can be quite significant, right? Okay, so again, just a quick overview. The ionization of water just essentially means, or the ionization of any substance just means how it breaks down into its constituent ions. So in this case, water will break down into the hydrogen ion and the hydroxide ion. In this case, water can release hydrogen ions and act as a base, act as an acid, or it can release hydroxide ions and act like a base, right? And again, so it can act as either a weak acid or a weak base. All right, so water is very unique in that sense, and molecules or compounds that can do that or that have that same ability are called amphoteric molecules or compounds. All right, so now let's talk about pH. So what is pH? Well, pH is a metric that we use to measure how acidic or basic a solution is, right? So pH is a metric we use to measure how acidic or basic a solution is. Okay, and pH is based off the concentration of H plus ions in solution. That's why it's pH, right? Because it's based off of the concentration of hydrogen ions in solution. Now, the concentration of hydrogen ions is denoted by H plus in brackets. So going forward, we're going to use that to basically represent the concentration of hydrogen ions. And this concentration of hydrogen ions is represented in, the units to represent the concentration of hydrogen ions is molarity, right? Because remember we mentioned that one of the ways we quantify things in chemistry is through molarity, and molarity again is the number of solutes in a solution divided by the liters of solvent. And molarity essentially just gives us an idea of how concentrated a solution is with the specific solute, and the solute in this case being hydrogen ions. Okay, now the formula for pH, so pH equals the negative log of the hydrogen ion concentration. So this is what pH is, right? And that is the formula for pH. So now let's break it down and kind of explain why the formula is the way it is. Well, we already discussed the hydrogen ion part, right? Because pH, that means it takes into account the hydrogen ion concentration. So in this case, the solute that we're focusing on is the hydrogen ions in solution. Okay. Now let's talk about why do we use a logarithmic function and why is it a negative? So the reason we use the log function for pH is because the hydrogen ion concentration in solutions can vary greatly, and logarithms help to compress that range. So let's talk about what we mean by that. So let's look at an example here, right? So if you look at the concentration of hydrogen ions in pure water, it's equal to 10 to the negative 7 molar. Okay? Now if you look at, say, the hydrogen ion concentration in 1 molar hydrochloric acid, it's a very strong acid, right? That's going to be 1 molar. And the reason it's 1 molar again is because hydrochloric acid is a very strong acid, and strong acids will dissociate completely. So 1 molar hydrochloric acid will result in 1 molar hydrogen ions and chloride ions, right? So it's because they dissociate completely. And so then again, the hydrogen ion concentration is 1 molar. Now on the other side, so if you look at the hydrogen ion concentration of a strong base like sodium hydroxide, so say we have 1 molar sodium hydroxide, that's going to be equal to 10 to the negative 14 molar. And the reason again is because all of this, because it's a strong base, will dissociate into sodium and hydroxide ion, right? And the hydroxide ion is going to combine with the hydrogen ions in solution, taking them out to the ultimate result is the resulting concentration of hydrogen ions is going to be very low, because you're not going to have that many free hydrogen ions, because these hydroxide ions are going to combine with the hydrogen ions to form water. So now, as you can see, the concentration of hydrogen ions in various solutions can vary greatly, right? Because again, these are to the power of, right? Which means like the number of zeros. So there's a large scale across which hydrogen ions exist in different solutions, and so that'll be very difficult to represent. And so that's why we use the log of the hydrogen ion concentration, because it allows us to compress that range. Okay. So now let's talk about why is it negative? Why is it the negative log of, right? Well, the reason it's the negative log is because the hydrogen ion concentrations in most biological systems is less than 1 molar, right? So in biological systems, the hydrogen ion concentration, for the most part, right, not 100% always, but for the most part, is always around less than 1.0 molar, right? So which means that in most biological systems, if we just take the log of hydrogen ion concentration, say pH was just this will always be a negative number. Because again, that's just how logs work, right? If if you take the log of a number that's less than 1, so say for example 0.1 or 0.001 or 0.0001 and so on, the net result of this logarithmic function is going to be a negative number. And so we don't want that, right? We don't want to represent pH as a negative, because that just wouldn't make sense. So that's why we negate, or we add a negative sign, because this will not, this right here will be a negative, right? Because in biological systems, again, because most biological systems have hydrogen ion concentration less than 1 molar. It's less than 1 molar, meaning it's a decimal, right? This is going to punch out to a negative. So if you put a negative around a negative, that's going to allow us to have a positive, right? Just the functions of, or the, I guess, the laws of math. But it's going to net a positive, so that means pH will be a positive, right? So that's why the formula is the way it is. And now let's talk about the actual pH scale, and talk about acids versus bases and so on. So let's talk about the pH scale. So the pH scale runs from 0 to 14. Okay, so this is kind of the range of the pH scale. So if we break this down, so let's break it down into 3 categories. So if the pH is less than 7.0, what that means is the solution is an acid. Okay, now if we have pH greater than 7, that means that the solution is a base. Okay, and then if we have a solution that is pH equals 7, like water, for example, this, or pure water, the solution is neutral. Okay, now we talked a little bit about it here. So if you look at here, so if we said pure water, right? Pure water has a pH of 7. 1 molar hydrochloric acid will actually have a pH of 0 because of how strong it is. And then 1 molar concentration of sodium hydroxide will have a pH of 14. So we said this is neutral, right? pH of 0 because it's less than 7. pH is less than 7, that means this is an acid. And then pH of 14, pH greater than 7, and that means it's a base, so it's a base. Okay, so if pH is less than 7, it's an acid. If pH is greater than 7, it's a base. And if pH equals 7, then it's neutral. All right, so let's talk about kind of, I guess, patterns regarding the pH scale and what they mean. So the lower the pH, right? The lower the pH, the higher the hydrogen ion concentration and the more acidic a solution. Okay, so the lower the pH, the more hydrogen ion concentrations are present in solution, which makes it more acidic. So if you look here, 0 is about as low as you can go on the pH scale, right? And if it's 0, that means there's a lot of hydrogen ion concentration in solution, because again, strong acid, everything dissociates, so it's just all hydrogen ions, 1 molar hydrogen ions in solution. So it's very high hydrogen ion concentration, which means that it's going to be very acidic. Now on the flip side, if you have a higher, if you have a higher pH, so the greater the pH, the lower the hydrogen ion concentration, and the less acidic, right? So the less acidic a solution slash the more basic a solution. Okay, so those are kind of the key sort of, I guess, relationships or patterns within the pH scale. So something that's very important to note, which sounds pretty counterintuitive, is that a 1 point change in pH is actually equal to a 10x change in hydrogen ion concentration. So let's look at an example, right? So if you look at an example, so if you take, say, for example, negative log of, say, the hydrogen ion concentration is 0.1, okay? We have another solution where we have hydrogen ion concentration of 0.01, right? So if you look at the difference between the hydrogen ion concentration in this solution, which is, I guess, 10 to the negative 1 power, versus this solution, which is 10 to the negative 2 power, right? That's a 10-time difference between the two. This is 10 times more concentrated than this solution is, right? Or this solution is 10 times less concentrated than that solution. So the difference here is a 10x difference in hydrogen ion concentration. But if you look at the pHs, if you plug this into a calculator, right, the negative log of 0.1 is going to net you negative times negative 1, which is equal to positive 1. So it's going to have, this solution is going to have a pH of positive 1. Now on the flip side here, we have the negative. We'll have the log of 0.01 is equal to negative 2, and so you have positive 2. So this right here is the pH, and this is the hydrogen ion concentration of the respective solutions. So if you look, the difference in pH here is just a matter of, the change is a matter of just 1, right? But if you look at the change here, change is a matter of 10. So as you can see, a single point change in pH will result from a 10 times change in hydroxide ions, which means that a solution with a pH of 1 point higher then the other one is going to be more or less concentrated, and we'll explain that in a little bit here. So you just have to really understand this point, because it's fairly counterintuitive, right? Because you're going from 1 point to 10 times. It doesn't make sense, but as you can see in this example, it does carry over and it does make sense. So now let's talk about changes in pH. So we talked about the lower the pH and so on, or the greater the pH. Now let's talk about changes in pH and what that represents or what that means. Well, as you saw here, if we have, say, a decrease, so let's look at it this way. So if we have a decrease in pH, which means we're going from this solution to that solution, right? A pH of 2 to a pH of 1. So if you have a decrease in pH, that means that you're going from a solution that is less concentrated to more concentrated hydrogen ions, right? So a decrease in pH is actually, it means an increase in hydrogen ion concentration. Okay, again, like we said, we're going from pH of 2 to 1, so that's a decrease in pH, but that means that you're going from a solution that has only 0.01 molar concentration of hydrogen ions to 0.1, so there's an increase in hydrogen ion concentration, as you saw. On the flip side, if we have an increase in pH, that means a decrease in hydrogen ion concentration. Okay, so let's look at it again. So let's look at now, remember we said this is an increase in pH, so we're going this way, right? We're going from a solution that is pH of 1 to a solution that's pH of 2, so you're increasing in pH, right? Increasing in pH, but if you look here, the hydrogen ion concentration is going from a greater concentration of hydrogen ions to a lower concentration of hydrogen ions, so you have a decrease in hydrogen ion concentration, right? So these relationships sometimes are inverse, because you have a decrease in pH means increase in hydrogen ions, and then over here you have low pH, that means you have high hydrogen ions in solution, and vice versa. So pH, so I guess you could say ultimately pH and hydrogen ion concentration have an inverse relationship. Okay, so that's very important to know. So now let's keep going and talk about why is pH so important in biological systems. So why is pH so important? Well, pH is important because it can influence the shapes of molecules, right? So pH can alter or influence the shapes of molecules. And we discussed this earlier, that the shapes of molecules in biology determines their structure. Their structure and consequently their function. Right? So because pH can influence the shapes of molecules, that means it can also influence the function of those molecules, right? And so that means that because, again, the function is dependent on pH, pH is of profound importance, especially in biological systems, right? Now, many biological molecules can have charged groups, right, which can interact with those hydrogen ions in solution, and which means that their structure can often be altered by changes in pH. So let's look at an example of what we mean by all this, right? So if we look at, acetic acid, for example. So say we have acetic acid, so CH3-C double bond O, OH, right? Now, here, say in solution, the hydrogen has dissociated and we end up having acetate, right? So we have acetate with a negative charge in the oxygen because the hydrogen had dissociated. Now, this is a charged molecule, right? Now, say that, you increase the pH of the solution that this is in by adding hydrochloric acid or whatever it might be. What can happen is the same molecule can accept a hydrogen ion solution and change to acetic acid, CH3C double bond OH, right? And this is an uncharged molecule now, right? So what that means is that you went from a charged molecule which can interact with water, right? Because charged molecule polar interact with water, to a molecule that is uncharged and non-polar / hydrophobic. Right, so as you can see, and these two solutions might have different pHs, so there might be a delta difference in pH between these two solutions. So just by changing the pH between these two, you go from having acetate in its charged form, in its ionic form, which can interact with water, to then having a hydrogen ion come along and bind to this oxygen anion in acetate, forming acetic acid. And so now you end up having an uncharged molecule which is now hydrophobic and cannot interact with water, right? Or cannot interact in a hydrophilic manner anyway. And so, as you can see, pH is very important because it can again alter shapes and structure and consequently their function in terms of the molecules, biological molecules. And so, the big takeaway is that it's very important for biological systems to maintain pH within a certain range, right? So it's very important to maintain pH within biological systems because fluctuations can alter the shapes of molecules and consequently their function, or their ability to function, as they normally would. And again, this maintenance of pH is a form of homeostasis. Okay, so now let's finish off this video by talking about buffers, which are a way to maintain, which are solutions or sort of a mechanism to maintain pH within a certain range. So let's talk about buffers. Now let's talk about buffers. So what are buffers? Well, buffers are solutions that maintain a relatively constant pH even when substantial amounts of acids or bases are added to them, right? So they are solutions that maintain a relatively constant pH. All right, and so the addition of a given amount of acid or base will result in a smaller change in pH in a buffered solution versus in a solution that is not buffered. Okay, so how do they do this? Well, buffers, what they do is they're able to maintain this relatively constant pH sort of range because they're able to readily absorb excess hydrogen ions or hydroxide ions in solution. So they do this by absorbing hydrogen, or I should say excess hydrogen ions and hydroxide ions in solution. Okay, and so in order to do that, buffers typically are made up of a mixture of a weak acid and its corresponding base, or a weak base and its corresponding acid. All right, so buffers are made up of either a combination of a weak acid and its constituent base, or a weak base and its constituent acid. Okay, so and what that allows, buffers to do is that they keep the body's pH within a narrow range that's needed for survival, right? Maintaining homeostasis with respect to pH. So let's look at kind of the famous example that we have in our bodies, specifically the one we have in our blood, which is the bicarbonate buffer, the carbonic acid bicarbonate buffer system. Okay, so let's look at an example. So we have, so let's go through this. So what happens is, we'll have carbonic acid, which is H2CO3, which is a weak acid. Okay, oops. And its constituents are, so when carbonic acid breaks down and dissociates, again, is a weak acid, so it doesn't completely dissociate. In other words, not all of the carbonic acid molecules in a solution are going to be dissociated, but the ones that do dissociate will dissociate into the hydrogen ion, as well as what's called the bicarbonate ion. Okay, so this bicarbonate ion is your constituent base. Remember, we said a weak acid or constituent base combination is what makes a buffer, or vice versa, right? In this case, we have a weak acid, which is carbonic acid, and you have its constituent base in solution, which is the bicarbonate ion. Okay. So now let's look at a situation where we have, so let's say this is in solution, right, with water or whatever, and now let's say we add acid to the solution, and let's see what happens when we add acid. Well, if we add acid, and I'm talking about a strong acid, say like, hydrochloric acid, so say we have, we add hydrochloric acid to the solution, right? So remember, we said strong acids will dissociate completely, which means that this is going to break down into hydrogen ions and chloride ions, right? So now we have additional hydrogen ions that are entering this system right here, this solution here. So now what happens is the hydrogen ion concentration will go up, right? Because you're adding acid, okay? So this is we're talking about strictly a situation where we add acid to a buffer. So when you add acid, what happens is if more acid is added, the concentration of hydrogen ions will go up, right? So that's what we expressed here. This hydrogen ion concentration goes up. And so what happens now is more of these bicarbonate ions are going to latch onto and accept these added hydrogen ions, right? So you have these bicarbonate ions, you're going to accept this added hydrogen into the solution, and that's going to produce more of carbonic acid, right? So what's going to happen is this bicarbonate ion is going to accept this added hydrogen ion, and it's going to form carbonic acid. And in doing so, what this bicarbonate ion does is it's removing these free hydrogen ions in solution, thereby preventing this addition of hydrochloric acid from changing the pH. Because remember, pH is the negative log of the concentration of hydrogen ions in solution, right? So if we add acid, this concentration goes up, which means the pH will go down. Because remember, we talked about that; it's inverse, right? So the hydrogen ion concentration goes up, which means pH goes down. But what happens is this bicarbonate ion is going to grab onto or accept these hydrogen ions, right? It's going to readily accept those, and so what that's going to do is it's going to decrease the hydrogen ion concentration in the solution now, right? Because you're not going to have free hydrogen ions floating around anymore because it's going to grab onto those, and so you're going to decrease this concentration. And if you decrease this concentration, the pH is not going to lower as much as if if this wasn't there. Because then if this buffer system wasn't there and you just add hydrochloric acid, the pH is going to drop significantly, right? Because you're adding significant amount of hydrogen ions into the solution. But now that you have this bicarbonate ion grabbing this, the change in this hydrogen ion concentration is going to be less, right? It's going to be less added to, there's going to be less free hydrogen ions floating around in solution, which means that the pH isn't going to change as much. Okay, so what ultimately will happen is when you add acid to this solution, to this carbonic acid / bicarbonate buffer system, what will happen is the reverse reaction is going to be favored, right? Because bicarbonate will combine with the hydrogen ions, the added hydrogen ions, forming carbonic acid, so the reaction is going to go in reverse. So here, the reverse reaction will occur. Okay, so again, if more acid is added, meaning the hydrogen ion concentration goes up, what happens is bicarbonate will accept it and produce more carbonic acid. And so not all of the hydrogen ions from the added acid will remain in solution, because some of the bicarbonate will accept some of them to form carbonic acid, thereby decreasing the acidifying effect of the added acid and ultimately reducing the change in pH that results from the addition of this acid. Okay, so now let's look at what happens when we have the addition of a base. All right, so now let's look at what happens when we have the addition of a base to this buffered solution. What happens is if we have more base added, right? So say we add, I don't know, sodium hydroxide, right? It's a strong base, so sodium, say we add sodium hydroxide to the solution, what's going to happen is, this is going to, again, strong bases will dissociate completely. You'll have sodium ions and hydroxide ions floating in solution. And what will happen is, now what happens is, these free hydroxide ions, what are they going to do? They're going to go ahead and grab a hold onto these hydrogen ions in solution and remove, sort of, and deplete these hydrogen ions in solution, right? Because OH is going to combine with this and form water, right? H2O. And so this concentration of free hydrogen ions in solution is going to go down, right? And so what happens is, if this goes down, this reaction is going to start to proceed in this direction, in the forward reaction. Why? Well, because you want to replenish the hydrogen ions that are depleted by this, by these additional hydroxide ions, right? By the addition of the base. So again, the hydroxide is going to latch onto this, or it's going to accept this free hydrogen ions in solution, thereby decreasing the concentration of free hydrogen ions in solution, and ultimately changing the pH, right? Its pH is going to shoot up. But what happens is this carbonic acid is now going to detect that, and it's going to push the reaction into the forward reaction, and ultimately more of this carbonic acid will dissociate to try and replenish the stock of hydrogen ions in solution, to try and counteract and replenish those hydrogen ions that are lost to the addition of this base. So again, the ultimate result being that it's trying to limit the change in the pH of the solution when you have additional base added. Okay, so again, overview, if we have more base that is added to the solution, what's going to happen is that you're going to have greater concentration of hydroxide ions, right? And what will happen is more of this carbonic acid will dissociate to counteract the combination or the combining of hydroxide ion with these free-floating hydrogen ions, thereby replenishing some of the free hydrogen ion concentration that's lost to OH minus accepting it, thereby, again, ultimately reducing the change in pH. All right, so in this case, when you add a base to this carbonic acid bicarbonate buffer system, what will happen is the forward reaction will occur. Okay, and so that's how this buffer system works in our blood. Now, something that also happens with respect to us in humans specifically, when you have lots of acid added, right? So you say you have a lot of acid in our blood. What's going to happen is it's going to cause, again, the hydrogen ion concentration shoot up, and what will ultimately happen is these bicarbonate ions are going to combine with those free-floating hydrogen ions, again causing this reaction to go in the reverse direction, right? Because remember we said if acid is added to the system, it'll cause a reverse reaction to occur. So now if we have really strong acids in our blood, and say the pH drops significantly, what will happen is these carbonic acid sort of molecules can actually break down into water and carbon dioxide. And so what actually happens is when we have hyperacidemia in our bloods, what will happen is we'll end up hyperventilating. The reason we hyperventilate is because, again, you have a lot of acid in our blood. A lot of these bicarbonate ions are going to combine with those additional excess hydrogen ions, forming carbonic acid, right, in the reverse reaction. And then what ultimately happens, this will break down into its constituent of carbon dioxide and water, and we keep breathing and we hyperventilate to try and get rid of this excess carbon dioxide. And the more carbon dioxide we get rid of, the more this reaction will get pushed this way, the less and the more free-floating hydrogen ions are going to be taken up by this, and thereby limiting the change in the pH that results as a result of this, highly acidic blood. And so that's what happens with buffers, and specifically buffers within our body, right? So again, overall, the main point of buffers is to allow there to be a buffer against changes in pH, right? So its purpose is to maintain a relatively constant pH in our bodies, to maintain and sustain life, basically. All right, so I think that's it for this video. Let's just make sure we covered everything. So we did talk about the different ways to quantify things in chemistry, right? We talked about moles and Avogadro's number. We did discuss what acids and bases were, and we talked about pH and why it's so important in biological systems, and then we also just finished off talking about buffers. So I think that's all of it for this video. So as always, I hope you guys learned something, and as always, stay true, be kind, and never stop learning. Okay, bye!